Hello, my name is Seiji Shah, and I'm here with Thomas Cohn to present our final project, Cooperative Slung Load Carrying with Quadrotors.
A common strategy for transporting large objects to remote location is to carry them by helicopter, and carrying the objects underneath the helicopter is a slung load, supported by tensile cables. We want to consider using quadrotors instead. This can increase the lift capacity as the quadrotors can cooperate. They can also exert more forces on the load, and it provides redundancy in case one of the quadrotors fails. However, this scenario presents many challenges. There are multiple sources of underactuation. The quadrotors themselves are underactuated, and also they can only exert a pulling force on the object. Furthermore, this system exhibits hybrid dynamics. If one of the cables goes slack, then no force can be applied in this state.
The state of the quadrotors are their position, velocity, orientation, and angular velocity, and the state of the point mass is its position and velocity. Each cable is given the same length L, and when the distance between the quadrotors and the mass exceeds that length L, the cable will stretch like a spring. The quadrotor dynamics will follow as standard Euler dynamics would for three-dimensional quadrotors.
In order to find fixed points for this complicated system, we use nonlinear programming. We can transcribe the problem of finding a fixed point as a non-convex optimization problem. We also need several tricks to make this work. We add a quadratic cost on the state and on the control, and also we enforce a minimum distance between the quadrotors, require that the cables be in tension, and that the control signal respects the input limits. This allows us to stabilize the system with finite horizon linear quadratic regulator. The stabilization is very robust, even across mode transitions. Even if the quadrotors are initialized with all four cables slack, the system is able to converge into a stable configuration. Note the necessity of using finite horizon rather than infinite horizon due to the insufficiently accurate numerics of SNOPT. We can also do naive trajectory optimization with SNOPT. In practice, it stabilizes quite well, but we can only obtain very basic trajectories. This trajectory has only basic constraints, input limits, and no objective cost.
Our system preserves the differential flatness property, where we can specify an output map to an output space that presents no coupling between the output variables. We can solve a convex trajectory optimization in the output space instead of a brittle non-convex optimization in the state space. Our output space consists of all but one tensile forces, all of the yaws of the quadrotors, and the position of the mass. The intuition behind the state solve from the output space is to solve for the remaining tensile force and then use all the tensile forces to compute the center of masses of the quadrotors. We can then apply the differential flatness property of the 3D quadrotor dynamics to solve for their states and controls.
What we then do is define a set of waypoints and times in the output space and solve a quadratic program to find a degree 7 piecewise polynomial trajectory that passes through these waypoints. We then apply our differential flatness machinery to solve the corresponding state and control.
The differential flatness property of our system enables us to plan more aggressive trajectories.